Good morning. Class looks very quiet today. So the homework assignment 3 solution should be passing around in your handout. Your homework assignment, please pass it to the front. And I sent the email about the makeup exams. If you have any questions, drop by and talk to me. Okay. So we'll continue back with the paging and virtual memory and the similar memory management techniques, right? So do you have any questions so far with what we covered? So the topic today is we look into virtual memory, which we kind of talked about it when we were talking about paging, and we talked a little bit more on what are the hardware, software, how the interaction happen, right? When we talked about paging, we said things can be swapped in and swapped out, and I kind of alluded to the notion of making the pages read only, write only, and do stuff, right? So the idea, like with the virtual memory, is once you have paging, once you have swapping and moving page between disk and the main memory, you're not forced to have your virtual memory and the physical match, right? They could be of different sizes, and you can bring them in and out. So essentially, you can make your logical space as big as you want, and you just need space for one useful page, so you can keep swapping them in and out, right? And of course, you don't want to have one, then your performance will be really bad. So we'll see how you go about doing some of this stuff, and what you need from the hardware and what the software, what the OS would do. The first idea is demand paging. So you use the invalid bit, and essentially if you have a page, if it's not there, the hardware has to let the OS know somehow, and the OS has to do something, satisfy whatever the hardware wants, and then restart the instruction, right? So here's sort of how we solve that. So in a page table, you have to leave a some entry to tell the hardware whether the page is valid or not. And so once that is set, when the application is running, right, when it hits one of the pages which has an invalid bit, the hardware will interrupt the OS. Till then, the OS doesn't get control. So once that happens, the OS has to figure out what to do. And what to do might depend on what you access. If you access something which is beyond the limit of your logical address space, then the OS may kill the process, give you a segmentation violation, or what have you. If you hit something within your logical address space, then the OS has to read it from somewhere allocated depending on what you're trying to do. So if you're trying to allocate a text segment, your program code, it probably has to read it from your program. If it's a memory page, then it has to allocate, or depending on what it's trying to do, it'll have to do something. And then once it's done, it should give back control to the hardware, right? And the key thing here is once the hardware gets control, it has to restart and do the same operation again, right? And again, a pictorial way of saying the same thing. So if you have a process with the logical address space over on the left, A, B, C through H, right? And its page table only has 3 valid entries. So if you access anything beyond that, if you access the page table 1, logical page 1, right, it's invalid, so the hardware will tell the OS. OS has to figure out what to do, place the page somewhere, and then change the bit to valid. And here's the actual algorithm of how things will work. And I'm gonna go to the pictorial representation, and in your handout you have the textual form, right? So essentially, you can follow along with those little numbered circles. So when an instruction hits a memory page, right? If it's invalid, which is step 1, right? You get a trap. You get a trap into the operating system, and operating system has to keep some tables which figures out what is free and what pages are being used, and what should happen for that particular page, right? So suppose it figured it has to come from a backing store. You'll do a disk read, have the page read, put it into a free frame, right? Once that finishes, the OS will be notified. So we haven't looked at the hard disk, how it happens in detail, but essentially any I/O after it finishes, you get an interrupt saying it's done. So once that interrupt happens, the OS will go back and notice that this is an interrupt which is for a page which is being read for a page table. So it'll set the valid bit on that particular page and let that process go, right? We kind of talked about it before, but essentially this is the whole way of how this happens. And the key here is once the OS gives back control at 6, the hardware has to have mechanism to restart the instruction. So it can't go back to the next instruction because it couldn't finish it. So it has to start from what it left off and redo it again, right? So that is not necessarily a trivial task. So if you have instruction, for example, like something like this, it's an assembly equivalent of something like this, right? Which reads a variable B, variable C, and then computes something and puts it into A, right? In the worst case, you can actually have 3 page faults, right? You try to look for B, it's not there, you get a page fault, you go through the whole thing, read some page in, and you find out that you really need B and B is not there, you go through the whole thing, and then you do A, you don't find it, you go through the whole thing, right? So in this particular case, so the OS cannot write anything into A till all of them happens, right? So it has to somehow atomically keep the B and C and A appear like there's no side effects, right? In this case, it's more easier to make this happen than other cases. One of the other cases, there are instructions which can copy a whole chunk of memory from one location to another location. So you can have something which copies this whole segment into here, which may actually translate into multiple pages, right? So if you were to copy this whole stuff from here to here, you may run into page faults along the way, you may run into page faults along the way. So when you restart, you have to restart from copying what you left out, right? Unless you make sure these are all atomic, right? You could end up with a case where you copied this part and then somebody else overwrote it while you're paging this stuff in, kind of thing, right? So when you have instructions which kind of span across multiple pages, you have to know what would happen. Even in the case of small, if you have like a long, right? If you have like a 128-bit long or something, it could be in 2 different pages, so you have to make sure you get the pages all together, right? So restart in these cases would not mean like restart and copying back from here, but copying back from where you left off and other mechanisms. So whatever the hardware provides, you have to do, but it may not be as trivial as just restart and do it over again, right? So if you say A equals B, this probably won't be as hard as something of this nature. And real machines like VAX and stuff used to have it even more complicated, where these could be overlapping, right? So you can kind of copy this into here, right, where things are overlapping. So you kind of assume that these are sequentially being copied from here to here, but the pages that they access and pages which are in memory would act in strange ways. But the hardware has to provide all the stuff. So whatever hardware can provide, the OS can do. But if the hardware does not provide a way to restart the instruction, you can't do any of these, right? Because when you fail, then you can't go back and redo the whole thing again. Over the years, OSs have looked at different ways of solving this problem. So one of the things that they can do is they can try to make sure that all the pages that the instruction would use, you get a fault all at once, or you get a fault consecutively, and you expect it to bring all these pages in before the instruction can start. And if you do that, then you have to make sure that none of these pages get replaced. Right? We'll see what replacement is in a couple of slides. But essentially, if you don't have free frame, you have to throw something out. And the worst thing you can do is throw these pages out. Right? You're trying to bring this thing so you can have this instruction, but if you start throwing the pages out before it completes, then this instruction would never finish. Right? So those are some of the stuff, and all of them depend on what the hardware can do. So throughout this module especially, I hope you realize that there are some things that the OS can do, something that the hardware can do, and it's important to realize what can do what, right? It's OS's job to figure out how to create this notion of a free frame. So OS's job to make sure that the I and B, the validity bit is set properly. It's OS's job to figure out what should do with the page, right? It may have to go to the hard disk. It may have to just find a free frame, empty it out, and give it to you. So if you're asking for a memory, if you're doing a malloc kind of thing, right? It doesn't have to read it from the disk in the first time. It can actually zero out the page and give it to you. So whatever that is, the processor does not really care. All it cares is when you get a page fault, you do something, and at the end you set the bit to valid, and it will restart, right? And we'll see what are some of the policies of how the OS can figure out what pages to replace, what pages to bring in, and all those things in this chapter. So essentially the point here is the page replacement policy, right? So when you come here in this stuff, when you trap in, you have to find a page to bring stuff in, right? So you have to do page replacement, which means that you need to throw whatever is in the page off the disk and bring some new thing in. And depending on how you do this, depending on which ones you bring, you may get good performance or bad performance, right? So in this case, it should be obvious. If you're trying to do this stuff and you only have, say, one page, right, your system would be terrible, right? Every instruction would get a page hit, and then you'll bring the page, and you'll replace the wrong page. So actually, you probably may not be able to make progress at all, right? If all of them happen to be in different pages, right? You get a page fault for B, you try to read it, then it becomes invalid, and then you try to get a C, that becomes invalid, but when you start it again, B is again invalid, so you keep going back and forth, right? So all the algorithms try to minimize this notion of how many page faults do you see, and if you think about it, this is sort of similar to what we did for the processor scheduling, right? You're trying to make sure that all the pages that you would want in the future are in your memory so you can make good progress, or all the CPU cycles that you want in the future are there when you want it without knowing the future, right? So you're trying to predict what the future would be, right? And again, there's a simple equation trying to show what the penalty would be, right? And this is sort of similar to what we did before. So if you assume a certain number of pages would fault and say a certain number of pages would be there when you want them, right? And if you call them the page fault rate of P, right, where 0 means no page fault, all the pages that you want is in memory. 1 means that every reference that you make is a fault, right? You have a simple equation trying to figure out what there should be. So 1 minus the complement of the probability, that's the amount of stuff that you go through main memory, right? For the stuff that you page fault, you have to add the cost of the page fault happening, the cost of moving whatever page is in there to the hard disk, and the cost of moving some new page, the old page back in and continuing. Right? So that's essentially the bottom half. The overhead, the cost of moving some page out, the cost of moving a page in, and the cost of restarting. And since you're talking about going to disk, this can be very slow, right? Memory operates in nanoseconds and stuff, disk operates in milliseconds. So page faults can really kill you. And so here's a typical example. So if you assume a 50% hit and 1 microsecond for memory and 10 milliseconds for disk access, right? So essentially your memory access time goes to 1 plus 15,000 times the page fault rate. Sorry, this should be the second one should be microsecond, right? It's 10 milliseconds, which is 10,000 microseconds. So it should be 1,500 in microseconds. Right? But your disk is the deciding factor. So if you don't have stuff in the memory, things will run slow, right? And this is sort of similar to what we did with the caching and stuff. Essentially, you're moving the stuff. The cache was trying to move everything from main memory into your TLB or different levels of cache. And here you're talking about moving stuff from hard disk, which is a very slow medium. Right? So is the general idea clear? We talked about this before, but essentially that's what we're trying to achieve, right? So if we do it right, then we can run many programs for the least amount of memory, right? The idea here is not all the functions are called, not all the program is used all the time. So you would benefit, you may not actually notice any performance degradation by having virtual memory, right? And that's sort of what we are trying to do with the homework assignment too, right? You'll notice that depending on the memory trace that you have, you may or may not feel too much penalty for bringing pages in and out, right? There is one necessary page in that you'll always have to pay, right? When the page is needed first, you bring it in. But if things work out, that may be the only cost you pay. You bring some page from disk, do what you have to do, and then write it out, but never bring it back in and forth. Right? So there are other benefits of what these things happen. Other benefits of this virtual memory notion where things are not brought in from disk into memory till you want it. And we'll look at one now and one later, right? So this answers the question of what happens if you have so much physical memory that you don't need virtual memory at all, right? So suppose you have, I don't know, like 128 gigabytes or 1 terabyte of main memory, right? So if you have 1 terabyte of main memory, then you can virtually run most of the processes in memory. You don't need to do all this stuff. You can read all of them. So you can probably run many applications, and they can all fit into memory at the same time, right? Which is, even if you don't assume 1 terabyte, it's sort of happening in most laptops, right? How much memory do you have in your home PC or laptops? What's the sort of the maximum? Gig? So how many of you have more than a gig? How many of you bought a machine very recently, like within this semester? Memory is getting so cheap that, I don't know how much you paid for a gig, right? But gig is like $70, $80, right? So essentially it seems like if memory is so cheap and this penalty is so high, right? The penalty of going to hard disk is so high. So in this example, we're talking about 1 microsecond, but the newer memory can be much faster, right? So memory is getting faster, disk is not getting any faster, your processor is getting faster. So the worst thing you can do to your processor is make it go to the disk to swap in and out, right? Because you're essentially making it from 1 microsecond to 15,000 microsecond kind of thing. So the idea is, if you have lots of hard disk, lots of memory, then you don't need to do all the stuff. And if you don't need all the stuff, get rid of the virtual memory kind of context. So the two things where we will use virtual memory, even if you have enough memory, is copy and write and memory map files. Memory map files we'll look at when we talk about files, right? Memory map files is a nice way for you to make your file look like a memory chunk and operate on it like it's a memory, and have the disk writes happen magically behind your back, right? It's a cool thing, and you probably use it without realizing it. Some of you may have implicitly used it. So the idea of copy and write, it's very similar to some that people might have used in file systems, right? The campus-wide file system that we have can do this, but it's not turned on by by OIT for whatever reason, right? So some of you might have used NetApp at jobs or what have you, right? How many of you used what I'm talking about, where it seems to create a active backup all the time? If not, we'll look at it when you come to the file system process, right? So the idea here is sometimes you want to delay doing some work till how much time you can wait on it, and hope to get better performance. So one of the things we talked about when you're doing processes is when you do a fork, you create a copy of the parent process. So if a parent process was big, you're going to have to create an exact copy of the whole thing. And that could be a slow process. And more importantly, that could be a useless process, because the first thing you do after you do a fork is an exec. So essentially, you clone the whole parent, and then the first thing you did was wipe out the whole thing and do an exec, right? So to solve that, they added the notion of copy on write. So the idea here is when you do a copy, right, you only do a copy when somebody writes into the page, right? When something is written, you know that the copy has to be different. So the idea here is when you have a process and it gets cloned, right, into two ones, right? You make sure that you only do this copy when you need. So essentially, you have one copy, have both the processes look at it, share it, right, in such a fashion that if one of them writes into here, at that point, you make a clone of that particular page, copy what is in here into a different page, and make it go, right? So that way, you only do it when you have to. And for this, you need help from the hardware. The hardware has to tell you when you're trying to modify this, right? If the hardware does not tell you anything, then you can't do this. But if the hardware can somehow tell you that something is going to be modified, and the OS know about it, then it can implement something where the copying only happens when you need it, right? And it's very similar to the invalid bit. So now instead of having invalid bit, now you're having an invalid bit which also tells you whether it's a read access or a write access, right? So you would set the page to be read only, or the equivalent of read only. So when you try to do something which is not meant for, then you get a fault saying you're trying to write into a page which is read only. And at that point, you create a copy, make both of them read write, and then let them go. Actually, I don't have a figure for that. So does that make sense? So the same way like we had the I valid and invalid bit, now you're going to have valid, but you can say whether it's read, write. We'll see later on whether we can do execute also, right? If you can set more bits on the page that you want to operate on, then the OS can use that to implement other functionality. And one of the cool functionalities is to make sure that only pages, when they get written, you modify it. If people read it, nothing will happen. So OS can essentially clone a process very quickly, right? And when you have these bits, OS also uses it for other purposes. So if you're sharing code between two processes, they are set to be execute only, no write, right? So the processes don't modify the program. If they do, then the OS gets to know, right? So using these bits, the OS knows when something happens, and setting the bits the right way, you can implement a copy and write semantics. Does that make sense? Right. So again, I want you to remember that all the thing we are trying to do is whatever the hardware can do, we can use that to add functionality or do our jobs easier. There are some things that the OS cannot function without the hardware support, right? You cannot implement virtual memory without the ability to restart the instruction, right? You don't need copy and write. I mean, this is a nice feature, right? If you don't have copy and write, then essentially your OS would copy the whole pages and let them go, right? So this is a optimization to make the process creation faster, but it's not a necessity, right? Whereas the ability to restart the instruction is necessary for virtual memory to work. if you can't restart the instruction, then in software you can't do any of this stuff. But most modern processors give that functionality because it's so useful. So let's go back to the page replacement, right? We are talking about page replacement. So suppose there's one process here, and there is a page, process here, page here, physical memory page here, which is allocated to, let's say, process A, right? And now you want it to go to process B, right? So the essential thing you have to do is you have to put this into if I have a hard disk here, right, you have to store the content. So you have to make sure that nobody is using this page. So the process which is running, another process cannot be using this page, right? So you move this page to the hard disk, right? And then you move another page back in here, right? And these are not atomic operations, especially when you're talking about multiprocessors and stuff. So when you're doing this, putting it to the hard disk, this process may be rescheduled, and it may touch this page, in which case you stop and then restart the instruction and stuff. But the simple case is you write this whole page to the hard disk, and then you read your page, right? So PA is here, and so you bring that page into here and let it go, right? So next set of stuff, we are trying to see if we can eliminate some of this stuff, right? Whether we can eliminate having to write into the hard disk and read back from the hard disk, right? Can you think of ways where we can eliminate this writing into the hard disk? What are the when can we avoid doing this?
If process A is already in the hard disk and it hasn't been modified?
Yes. Yes, so if process A, if this page is already in hard disk and if it's not modified, right? So if it's not modified, then there's no point in writing it because you know for a fact it's not going to be modified. So you can just bring this in. So you can get rid of this one, right? So there are a number of cases when this won't be modified, right? Can you name one case where it won't be modified? When you know for a fact it won't be modified?
It's executable.
Yeah, if it's executable, if it's a program, then for the most part it shouldn't be. So even if you have no permissions and stuff, you can assume that executables are not written, so they would not be modified, right? Is there a way for data to be in that state? Depending on what the compiler and all does, you can put the data, some of the data, read-only data items into the read-only data page, in which case you wouldn't have to read, right? I think one of the examples I had was if you had in a program, if you call like this, right? In C, this memory is read-only, right? You can't do this, right? And you can't say, right? You're not supposed to do this, and in some systems you may be able to do this, but essentially this is a constant array, right? And you're not allowed to write into whatever was in that array, right? So essentially, if the compiler knows this, so it can create this into a read-only data segment, right? And if the OS knows that, then it knows that nobody can modify it, so it doesn't have to bring it back either, right? So those are the simple cases that the OS can take care of without doing what we're going to talk about next, right? These are facts based on how the programs work. So it doesn't have to do anything else. The next interesting case is this page is modifiable, right? But between the time it was created, between the time it was written and now it was not modified, right? In that case, we don't have to do it either, right? So for that, we need to know whether this page was modified since the last time it was brought in. not that this page was ever modifiable, but since last time it was brought in, right? So how would you do this stuff? Okay, how would you possibly do this? Some ways of doing this. How would you do this if you have hardware support? Or what kind of hardware support would you need for this to happen? Do you need hardware support for this to happen at all? Actually, that's a trick question, but let's stay with let's assume that you need hardware support, right? What would the hardware have to keep track for this to work? One is you have to set what the mode is, right? You have to set it to write, so you know it should be write only, right? And perhaps something like setting some bit to 0 when you bring the page in to say that this page was never written before, right? And the hardware would have to change that to a 1, right? The OS cannot do that. OS, all it can say is, when I give you control, I know this page is what I thought it should be, so I'm going to set it to 0, right? But when some instruction modified it, the hardware has to update this field. So when the OS looks at it, it can look at the bit and say, yes, when I gave this page to the processor, it was 0, meaning it was clean, but some instruction must have modified it, so it's set to 1. So any page which has a modified bit set to 1 and which is in the right state should be returned. Right? So that's a way for the. So again, keep in mind that OS does not have any control once it gives control to the processor. So unless the hardware marks these pages, the OS typically does not know how to do this, right? Can you do this in software without any of this bit support? Okay, the answer is yes. So how would you do this in software, right? I'm not worried about performance. I'm worried about how would you do this in software. Yes?
Manually check the entry memory against what's on the hard drive and
That's right. I mean, I said don't worry about
the hard drive to compare it.
Yeah, or actually have some other memory. If you have so much memory, right, then you have it somewhere else, and then so essentially when you're trying to replace it, you compare it with the whatever version you had and see if they match. If they don't, then write it, right? It's not as bad idea as you would imagine because hard disk is so slow, right? Hard disk is so slow. So if you have so much memory that you don't really need it, then this may be a good way to save on writing to the hard disk. So essentially, you create a copy of. So when the OS gives control back, it creates 2 copies, right, with the same contents. So when you try to replace it, you check at these 2 values, and if they are different, then you write, right? And if they're the same, then you don't have to write, right? So what are the benefits of software policy you can think of? What are is there reasons why the software approach might actually be good? Other than the wasted space, right? I mean, yeah, you waste space. Yeah.
You can support more hardware, and you can write an OS for multiple hardware platforms that support those mode bits.
Yeah. So one of the things is you don't need the hardware to support the stuff. So you can have this work on OSs where it's not supported, right? Again, it's not an efficient way, so you need to have more memory and stuff. Can you think of other ways why this may actually be better? I'll give you one hint, right? Think of multiple, think for a long time. Think this page is being there for a long time.
If you ever need to run like a procedure or something again, you can identify that untouched copy is the same thing. You wouldn't have to copy it again from the hard drive.
Oh, you mean like use this page?
Yeah, I guess. You
I suppose you
can
could.
actually keep more stuff around. But you wouldn't have to make it.
Yeah, I hadn't thought of that one. But that may be a way, that may be something like sort of like your copy and write kind of thing, right? So essentially, you know you are reading the same page in, and you know you're trying to, it's a modifiable page, so the new process which creates doesn't have to read it from disk, it can read the other copy you have, right? Systems I know don't do that, but that's an excellent point, right? But the other thing is think of the long term, right? So the answer, the key is in how would this bit be set, right? The OS sets it to 0, right? And the hardware can set it to 1 for under certain circumstances, right? We don't define what they are. You can think of all possible cases how the hardware can set it, right? But we know that once the hardware set it, the reason why the OS is trying to do this is if this bit is set, it knows it should be returned. It should be returned to the hard disk, right? Is there a way that the software can actually perform better in this case? Yes.
Well, if you implemented in software, it would be easier to tell why you were getting the trap rather than hardware. You only got a bit to go on. You don't really know why it returns. So if you have multiple reasons for it to be switched, you wouldn't know what the reason.
Can you think of a reason why?
Well, the reasons that it might not be able to go back to, there's arbitrarily many.
One of the reasons is if you write back the original value in software, right? If you say something like I equals j equals I, right, and then I equals j or something like that, right? I don't know. This didn't make sense, right? So basically, you copy the you copy the value and then write back the same thing, right? The hardware-based one, it does not know what the software is doing. All it knows is a value is written, not if the value was restored back to something it was, right? I should be able to come with an example, right? Yeah, something. Let's assume something like this, right? Let's say I equals 2, and then the OS gave control to the processor, right? And then the program changed it to 4, then it changed it to 2, then it changed it back to 4, right? So at this point, if you're trying to replace it, right? Actually, sorry, it should be I equals 2, right? Trying to replace it, then nothing really changed really, right? Yes, there were 2 write operations, but they canceled each other out. So if you're doing a software-based approach, then you can actually check to see nothing really happened. So you don't have to do anything. So, okay, is this example clear? Right. But if it's a hardware-based approach, the hardware cannot be made that complicated. You can't figure out what really happened in the memory location. So the only way you can do that is if it has its own set of memory pages, it doesn't do that. Right. So you may be able to avoid some of these things. And there are some of the reasons why some of the distributed shared memory machines are actually using software-based approach. And the fact that hardware did not provide it, right? The other thing you can do, which we haven't touched until we get to the other point, to the file section, is if you have a 8K page, right? Using a software, you could figure out that only this 1 byte was changed. Using hardware, you have no way of knowing what really changed. You have tried the whole thing, right? So in cases where writing small things are faster, if you have a software-based approach, you can just write this little thing rather than writing the whole thing, right? So there are different reasons why you want to do any of those. But again, the key thing here is you have a page which has to go, and you are trying to figure out what to do, but where it should go, and trying to avoid this right if you don't have to, right? And then you bring the new page in, and then you continue, right? And some of the ways you can do that is to have the modify bit or dirty bit, it's called different terms in different hardware. So essentially, it tells the OS something changed, and it can do the right thing. So here's more of a pictorial way of doing the stuff. So if you want, the first process has to kick something out. You look at the bit to see if it's modified. If it is modified, then you have to wait for the page to be returned, right? And then you have to read the next page in, and then you proceed, right? And a lot of race conditions here, right? Because you're essentially saying, okay, go right to the hard disk, assuming that the other process will never come in. Because if it came in, then it'll access this page, it'll become valid, it'll move back in and stuff. So the code for doing this is not as simple as we had in the graph, right? Because you may schedule to read a page, but before the page is returned, something else might have happened. Or if you try to schedule a write, at the end of the write, something else might have used this page, or things change. So you have to constantly. So you can go back to you can't predictably say this is the exact sequence of events which you'll take, right? So the next process is trying to figure out what is the best page replacement, right? And so essentially the idea here is, I want the page, and all the pages are being used. Which one should I take? And this is complicated by all the stuff we talked about, right? Different pages have different costs. So depending on what the cost is, you want to replace the cost which has the least penalty in the future, right? And like we said, read-only pages are cheaper than write pages, because write pages may have to be written to the disk and all those things. So you have to figure out what is the right policy, and that's the focus of the next few sections. But essentially the idea here is OS has to figure out something to move in, and you're trying to do a good job for the future without knowing what the future is. Again, the book has a lot of nice graphs. So essentially, you're trying to find a victim page, push it off to the hard disk, and bring a new page in. And like we said, the step one may be skipped if for the right set of pages. You don't have to put it on the disk, right? So I'll talk a little bit about what we're going to do, and then continue on the next lecture, right? So the way we analyze this is to you want to find an algorithm which has the lowest page fault ratio, right? And to kind of illustrate how these things work, you have a notion of a reference string, right? Which is sort of like what you're doing for the homework project 3, right? Essentially, you think of some page accesses or frame accesses, and try to see how your page replacement algorithm would work for that particular thing. And it's called a reference string. And that's a good way to try to figure out how these things work, right? Because real systems are much more complicated. Real systems see the references from multiple processors all at once to the processor. But this is an easy way for us to kind of understand how things work. And what we kind of expect is, as we increase the amount of memory on the x-axis, you expect a page fault ratio to come down, right? As you have more pages, you expect the pages to be brought in and stay there, right? So there will be a certain page fault rate to bring the pages in the first time. But if you have infinite memory, then you only pay the cost to bring it in once and no more, right? But if you have less memory, you expect to have more page faults. Does that make sense? Right? If I have infinite memory, I bring it in once and then I'm done. If there's less memory, then I would have to bring it in, replace them, and so on. But I would like them to be the fact that if I have more memory, then I do a good thing that I don't have to do more page faults than when I have less memory, right? So this is the sort of graph you want, and we'll see that it doesn't have to be this way, right? So let's look at first in, first out, which I think you'll do for your homework project too, right? So that's the reference string up there, 1, 2, 3, 4, 1, 2, 5, 1, 2, and so on, right? So when you have 3 frames, that's the order of replacement, right? Let's right. So you have 3 frames. The first one comes in, right? The replacement algorithm, you're doing first in, first out, right? So the first one would be 1, and second would be 2, and third would be 3, because they're all empty, right? And then 4 comes, right? So 4 would have to replace the first one which was here, so this will become 4, right? And 1 will come, it has to replace the first one which came, it will become 1, and then 2 will come, it will replace this to 2, and then 5 will come, this is the 5, and then 1 will come. 1 will come, but 1 is already here, 2 is already here, right? And then 3 will come and replace this, 4 will come, replace this, 5 is already here, and we are done, right? Yeah, so the end result is you have the 5, 3, and 4, right? I kind of overwrote here, and the slide kind of goes on the side, right? So essentially, you took 9 page faults if you counted, right? So this is how your first in, first out works, and this is how it will work for your project too, right? So you can again work through this for 4 frames. It's in the slide, right? So if you go through that, you'll notice that it faces 10 page faults, right? So essentially, what we wanted is not true on this case, because you actually have more page faults than you wanted. Then when you had lower memory. If you had 3 pages, you had only 9. But when you have 4 frames, you actually have 10 page faults. And it's called Ballard's anomaly. And there's a class of algorithms where this happens. And so it happened because you might notice that there was a time when 1 and 2 were being replaced. There's a little stack behavior happening, right? And it's called Ballard's anomaly. And this is again the same reference string goes through a thing, right? We'll continue with this with the page replacement in the next class. So, yeah.